So hello, KubeCon. So imagine a world where no phone buffers, and also no video call never get dropped, and over the phone, no gitch, no gitch. So, so how amazing that would be, no? So to deliver that kind of experience, our network need not only to be fast, it has to be smart. So this is the area where our work, the AI/ML framework from the O-RAN SC, play an important role. And today we are going to take a deep dive and try to understand how we are addressing this problem. Okay? So hello everyone, welcome for this session. Myself, Subhash Kumar Singh. I work as a senior chief engineer at Samsung Bangalore. This is our nice building in the Bangalore. And currently, I'm also the PTL in the AI/ML framework project. So that is in the O-RAN SC. And also, in the past, I have a decade of experience contributing to different open source like O-RAN SC, Nephew, ONAP, OpenDelight. So many open sources are there. And also, I would like to mention the photo of my team who is dedicated to deliver this framework. Okay. So as I understand, a lot of folks here does not come from the telecom background. They do not understand the telecom properly. So for them, I'll just set the context. I'll start this story from the RAN. So what exactly is the RAN? So RAN is a part of mobile network which actually connects your phone to the internet. Okay? So similar to any TCP/IP protocol stack that we have studied, similar to that, the RAN also has its own protocol stack. So the layers are RF, PHY, MAC, RLC. So these layers are there. So actually, that is responsible for transmitting your packets. So traditionally, it used to come as a single box. Okay, so that was neither cost-effective, neither you can take advantage of virtualization. So slowly, when the specification of the 3GPP, that is another one, SDO, standard body. So slowly that evolved. They proposed a lot of new split architecture for this functionality to keep in separate boxes. So there are total 8 options. So one of them is the 7.2 split architecture. So they try to split this functionality into the different box. And the thing what we get, the cost effectiveness, and also we can deal with the virtualization. So in that way, we have divided this function as here ORU, ODU, OCU, and each has a separate work of it. Like ORU, that is responsible for time-critical work like transmission, converting your audio signal to digital and digital to audio. ODU, that is for the scheduling purpose, schedule how you'll do the transmission. CU, that is for the session management and also for the encryption, decryption kind of work. So in that way it happens. Basically, if you would like to understand the telecom properly, this is my antenna. This phone is my antenna, okay? And that guy who sits there, who controls the mic, so that is the DU, distributed unit. And the person behind that who sees the overall thing, that is the CU, centralized unit, who checks the overall thing. So in that way, you understand how this protocol stack works, okay? Fast forward the story. 2018, the O-RAN Alliance, 5 of the prominent operators, they came together. They came up with one new initiative, O-RAN Alliance, so that they can develop the specification around the RAN, so that they can fulfill this requirement. They want to make a RAN intelligent, open, interoperable. So these 3 are the important pillars. So that intelligent means RAN should be intelligent enough so that I can use the AI/ML algorithms. I can optimize my RAN. Open means I'll provide the specification and standards, open the interfaces so that people could participate. It should not be the proprietary solution. And also then the interoperable. So operators wanted to break the vendor lock-in. They wanted They can take the product from the different vendors, and also they can do the mix and matches. So in that way, O-RAN Alliance is to trying to bring up the development with these pillars. Okay. Okay. Now we'll come to this architecture. So that is the output of Alliance. So this is the blueprint for any modern RAN which delivers openness and intelligence. So a few boxes you have already seen: CU, DU, RU. This already you understand. And apart from that, there is a few more boxes: SMO, Service Management and Orchestrator, non-arteric, near-arteric, and O-Cloud. Okay, so O-Cloud is the platform which avails you the physical resources. Over that, you can actually run your containers or any microservices, or you can run your workloads there. Okay, so RU, CU, or any near real-time rig, so that run as a workload. Okay, SMO. So it actually oversees the entire network, and it automates the things related to configuration, monitoring, and deployment. So there you can also see that there are different interfaces to do this work. So O-RAN Alliance is coming with a specification for each of the interfaces. So a lot of works are happening there. And the near-arteric and the non-arteric, they are responsible for optimizing your network. So where the intelligence actually runs in the form of RAP and XAP. Okay, so also I'll introduce you to the 3 control loops that exist in this architecture. The first one, real-time control loop. So non-arteric is responsible for that control loop. So it is something like I would like to optimize my network with some long horizon. So those kind of intelligence I will write it. Policy-related thing, I'll do it here. Model training, I'll do it here. Because those are non-time critical operation, and here the time sensitivity is more than 1 second. Okay, so the action will take a longer time. The next control loop is the near real-time rig. So that time constant is somewhere between 10 milliseconds to 1 second. Okay, so the XAP comes into the picture. So those actually takes the input from the higher level and try to dynamically optimize your RAN. So I'll give the example like suppose you would like to configure a bandwidth. So that you can do those type of things you can do at a near real-time rig. You can do the inference management. Those things also you could do it. And the closest loop that runs directly on the DU and the CU. So that is real-time control loop. So directly you fit the intelligence there, and those things kicks in. So example for that, suppose transmission-related error correction you would like to do. So those things you will do it here. So best way to understand. Let's say you are driving a car and suddenly you apply the brake. So those things are the immediate action you need to do it. So those are the real-time actions. So similarly in the telecom, we have those kind of actions also, okay? Okay, so now we are in a good position to understand what exactly the O-RAN does. O-RAN Alliance actually produces the specifications, and it avails for the implementation. So O-RAN SC, O-RAN Software Community, is the sister community of the O-RAN Alliance, and where the actually action happens related to coding, community. So things are happening in the implementation-related things happens over the O-RAN Software Community, and these go hand in hand. Yes, one guy develops the specification, and another community implements it. Okay. Okay, so now we are in a good position to understand what exactly the role of the AI/ML framework. We saw the architecture, right? So in the architecture, actually avails that you can run the intelligence in the near real-time rig and the non-real-time rig. Both combinedly, we call it rig, okay? We can run the intelligence there. So actually, we took this advantage, what provided in the specification, and we brought up the AI/ML framework, connecting those dots by providing the tooling for the model training, model deployment, performance measurement. So this all thoughts we thought around it, and we are providing those toolings. We are also building the pipeline and trying to do the training. And thing to note that What exactly distinctive feature AML framework has? Like you might be understanding that there are a lot of training platform. But why exactly I need the AML framework, right? Because we are trying to deliver a specification compliant, the framework which well understand the standardization. So that value proposition we are trying to bring it here. So it is compliant to O-RAN Alliance specification, and in that way we are providing a telco friendly who understand the telco properly, and we are trying to provide a framework for the model training. So yeah, thing is that it is a telco-friendly AML framework. And also what we are trying to separate out the business logic and ML logic separately so that a telco operator comes, they put their use case, they need not to bother about how the ML specific related codes, and they need to do it, okay? And this is the use case approach, right? So telco has a different kind of use case, like for example, I would like to dynamically manage my bandwidth. I would like to maintain the inference. I would like to create the policy. So based on the different use cases, we will onboard the use cases pipeline. And then we'll just ask for the data and also the input, what they need to do it, and we'll do it. And of course, that I mentioned, specification compliant implementation. So O-RAN Alliance that provides the specification, and still the lot of development is going on the specification side. And hand to hand, we are also parallelly developing our framework. And the last thing important to note that it is not only limited to telco. We are trying to design in such a way that it can be integrated with any network management system. Okay. So just note this point. We are trying to make a generic platform. Okay, and this is one complicated diagram that I have taken from the specification. So there is a small island which says that AI/ML workflow function. So the framework actually trying to address that particular ML workflow function. So you can see that non-arteritic box, near arteritic somewhere here, non-arteritic here, okay, and then SMO box. So we are trying to address model building, model deployment for both non-arteritic and near arteritic, and here actually AML framework would be situated, okay. And now I'll try to give you a complete execution of workflow, how exactly the thing will happen. And so this is the non-arteritic, okay? I'll just take an example of how we deal with the non-arteritic use cases. Non-arteritic means long-term network optimization, policy creation, ML model training, okay? So that kind of use cases. So non-arteritic is generally responsible to collect the data from the different sources, different G node B, different E node B. He will try to collect the data and keep somewhere in its own data lake. So that concept, actually we call it DME, data management and exposure. So what actually it does, it is a generic implementation so that a different producer could come and they can actually put the data there. And as a consumer of DME, we have to create only a job so that we can retrieve the data. Okay, so we'll start with those assumptions, right? Data is available at the DME, okay? And intelligence is there at the RAPs, okay? And what exactly here we'll start? Currently, in the previous release, this diagram is from our previous release. We are modifying. I'll come to those things later. So first thing, we'll start from the Jupyter notebook. In the Jupyter notebook, we write our pipelines, Kubeflow pipelines, okay? So that we onboard. That is the use case. We onboard it. And then we create a feature group, the step one, feature group. So that is something equivalent to data source, or it defines your data set, what you will do the training, okay? And we also have the PostgreSQL to store our metadatas, okay? And the step number 2, once we create the feature group, so that time we collect the data from the DME, which is actually InfluxDB for us. So InfluxDB actually collects the data in it's a time series database, right? So we have the time series data. Then Um, okay. Okay. So the next step is the feature extraction. Data lake has lot of columns, lot of data sets, right? So we are not going to build a model by all the data, right? We just filter the data. We do the feature extraction, which features are important for us. So those things actually we will extract it, okay? And this process actually we take help of Apache Spark. So we create the Spark data frame. We take the data from the source and keep in the destination. And also this data extraction part, we have made the generic so that you can use the different databases. Here I have given the example, influx to Cassandra. So you can use some different kind of database as a source and a destination also. So now you have your data available here inside our AIML framework. Okay. So this part is the AIML framework. Okay. And now the data is available, and okay, data is available. You have the training pipeline. Oh, 1 minute. Okay. So now here the Kubeflow kicks in. Okay. So now we do the training by the use of the Kubeflow pipelines. So data is available from the feature store, and the Kubeflow pipeline has all the logic related to ML, like which model you would like to use, and what kind of epochs you would like to use. So those things actually you could define it. Even the hyperparameters also you can define it. Currently in the pipeline we use the pandas. We take the data from the Cassandra and convert it into the pandas data frame. Okay, and using the pandas data frame we do the lot of transformation on the data, and finally we do the training. And once the model is computed, we keep it inside the LeoFS. So LeoFS is again object storage for us. So we could use the different S3 compliant object storage, but as LeoFS is the Apache 2.0 compliant, so we have taken this option. Okay. Okay, the next step, once the model is computed, what we'll do register the model in the catalog. So catalog is the model management service. So for us, so we will just onboard the model there, and you can see we use the S3 APIs just to keep the model again in the this model storage and in the catalog, and we'll just serve to any consumer. Okay, and now we are coming back to the model inference. Okay, so model inference service is where we would like to deploy the model. Okay, so when our model is computed, it is there in the catalog. Any consumer comes, he understands what he would like to deploy. He will create a case of service model. Case of service, and he will deploy the model. So here for the deployment we use the case of, and currently we deploy a TensorFlow model. Okay, so whatever we computed in the pipeline, so we were taking the LSTM model to compute, and finally we'll deploy it as a TensorFlow model. So once the model is deployed as an XApp and the RAP, so you remember I was talking about XApp that runs in the real-time rig, and the RAP which runs in the non-RT rig. So that is the intelligence that runs in the different layers based on the criticality. Okay, so in that way we do the model training and the deployment. And this is the holistic architecture for our ML framework service. So if you see it here, so we have the AI/ML management function, so that interacts with the training platform. So there we retrieve the data and we train the model. And finally, here you can see this part is the non-RT rig, and this is the near real-time rig. It is a time-sensitive deployment, and when we need a non-time-sensitive deployment, so that time we deploy it as a RAP. So RAP deployment, XApp deployment, both are managed by AIML framework. Okay. So just to explain it, so it does a simplified way of model management. It is a robust platform, and it is agnostic integration. Like if you have any network management system, you can also integrate. You take the data, you train the model. Okay. And now the thing, who is consuming and what are the use cases actually we do? So so we work as an open source. So there are different universities like NTUST, that's situated in the Taiwan. So they are also participating in this open source, and they do the UAV path prediction. So I think by this time you might be understanding that we only do the time series, we take the time series data and we do the model training. But here, actually what they did, they are doing the image processing. So a drone captures the images, and using that images, they actually train the model, and that they will take for the path prediction for their UAV. So here they are trying the image processing, and there's one more university, Kyunghee University from the South Korea. So they are doing the traffic forecasting. So they have the different data set from the airport, mall, and they are trying to do the traffic prediction. And also there is in the open source as a community, we are joined, and there is some TIMS operators data is available, so that we are trying to do energy saving modeling. So currently that is still in a discussion phase, not much action happened here. But yeah, these two things are active. You can easily find the reference in the, I have given the reference here. You can read the more details there. Okay. And now the demo part. So I have one pre-recorded demo, so just to help you to understand what things we do. Okay. I hope this should be. Sorry, seems not able to play it here. Okay, good. So yeah, so first thing, we register the model. So any model producer comes, he registers the model. He says that, okay, I have so and so model, and these are my feature list. I would like to train a model on this feature. Then what I do, I create a feature group. Okay. So feature group defines my data so that I can extract the data from the data lake. So that is currently in the non-arteric, okay? So I provide the details about from where you need to fetch the data, okay? So that I'm doing. And in the corner, you can see PDCP bytes, PDCP byte uplink. So these are the telco-specific KPI parameters that is generated from the network, okay? So that way I'm trying to do it. So I'm just providing the data source, okay? So these are the few low-level details. Actually, as we are growing as a growing in the project, we are slowly trying to provide the abstraction on it. Okay. Now feature group has been created. Okay, you can see the details. The features is now PDCP byte downlink. So it's again a telco-specific term. So just ignore it. Okay. Now we are starting the training. So in that for the training, we provided a training job name. So that matches with the model name here. And okay, so here we provided the measurement. So this is the way actually we describe our training. We provided the hyperparameter, how many epochs we would like to take it. Okay, and now we will do the training. We will starting the training. Okay, so training is created. So that is also in progress state. So there are different states like a data extraction. And then we do the training. Once the data is extracted, we do the training, and then we store the model also. Okay, so still that is in a progress. So you can see the training has started after the data extraction, and then yeah. So in the bottom you can see yeah, somewhere here you will find the model URL actually at the last. Okay, model URL. Currently it is empty. Okay, so once the model builds, that will fill. Okay, model is trained. Now you can find the model is available. So that model also you can download. Okay. Okay, so till this part we trained the model, we stored the model in our S3 object storage. Currently LeoFS for us. Okay, so I'll go to the next one. So where exactly we deploy the model? Okay, so so currently this example, let me stop it. Okay, currently in this example, actually I'm going to deploy the model in the near arteric as a XApp. And the previous diagram I was explaining you how we'll interact with the non-arteric. Okay, how we'll deploy it as a RAP. So few configuration actually we need to do to interact with the near arteric. So those details have been captured. Like we install the KServe, then we install the RIG DMS, full form deployment management system for the near arteric. So that we do. I think this I'll try to move it further. Okay. Let me try that. Yeah. Actually, some configurations are there, so I'll just skip it so that we can directly come into the. Okay. Okay, so here actually I'm at just configure the KServe, and then I'm trying started the RIG DMS. Yeah, I started the RIG DMS part, which is required to deploy the model. Okay, and then I wanted to show you the prediction, how we do the prediction. Okay, here the deployment happens. Okay, sure. So now we are going to deploy the model. Okay. So things we just set it up till here, okay, for the near arteric. Now we are going to deploy it. Okay. Currently no XApp is deployed. Now we are going to deploy it using this curl request. Okay. So you can see we have provided the inference service, and we have also provided the model name and the model version what we would like to deploy it. So now we are going to deploy it. Now we'll list the XApp once again, and we'll see. Okay. Okay, so here you can see. Yeah, here actually it lists like the deployment. Okay. Okay, so you can see now our model is running as a XApp, sample XApp predictor default. So now as a XApp it is running. Now the next thing, we'll do the prediction. So for the prediction, again, we need to provide last 10-second data, and we will predict the 11-second value. Okay, so those things we have configured in the this script. So the input QE.json that contains the values for last 10 seconds, and now we'll do the prediction. So here you can see this in JSON files we have 10 seconds value, last 10 seconds value, and we are just trying to run this script, and here we predicted the upcoming value, the 11-second value. Okay. Okay. So in this way we have the deployment part. And I'll just give the roadmap for the AML framework to you, how exactly we started. So in the January 2023, as a G release of the O-RAN SC, we started, the first time we participated. And as a H release, we added one feature to diversify the data source, so adding the non-arteric. And yeah, so in that way, we release by release, we are keep on incrementing. And in January 2025, we are going to have our latest release and the K release, and where we are targeting for the model retraining and specification alignment, and it's like how O-RAN Alliance produces the specification. So we are also trying to implement those things. And also now this AIML framework you can use from the non-arteric from the RAP. So that exposure in how the specification guides us. Based on that, we actually will do it. Okay. Okay. So now the future goals. So of course the specification is the most important part of us. We will be compliant to it, and develop a robust data pipeline to support the multiple data sources. Okay, currently you have seen the example with the InfluxDB, right? So we would like to support multiple data sources. And we would like to actually diversify the pipeline execution. Currently we support the Kubeflow. So in future we are looking towards the MLflow, Flyte, this kind of pipeline executors. And also, we would like to integrate closely with the non-arteric for the managing AI/ML application and automating the model lifecycle process. Okay. And the important piece still is missing for us, model performance monitoring. We deployed the model. Now we would like to capture how the model, is performing. And based on that, we would like to trigger the model retraining. So yeah, so we would like to focus actually in this part in our upcoming releases. So yeah, and this is our community details. So as part of the O-RAN SC community, we do our bi-weekly meeting. So that happens bi-weekly Tuesday 8 a.m. EDT. So this is the QR code for that. And yeah, of course, our wiki page is available here. You can try the installation. And if you find any issues or any problems, you can definitely report the Jira. That will be helpful for us to mature our project. And also, the code is available in the GitHub repo. And also, I would like to request everyone come join this community and also contribute. That will be helpful for us also. So that will be fun also contributing. Okay, and I would like to end my talk with our vision that we would like to build a scalable and intelligent integrated AI/ML ecosystem for the O-RAN SC community, so that we can drive the next generation telecom network we can develop around it. Yeah. Thank you, everyone. Yeah. So any questions? Yeah. Huh. Okay. Right. Right. Actually, we are maintaining one catalog. Okay, so I was mentioning that MME, model management and exposure. So once we train the model, right? So based on we calculate the accuracy from those metrics. Okay, and we document it here in the catalog. And if you go to the specification, you will understand there is a consumer RF or consumer XF. So he will go through the catalog. He will understand what are the models are there, how they are performing. Based on that, they will choose it and they will deploy for the request for the deployment. So there is a concept of producer, model producer, and model consumer. Okay, so consumer will choose it. Okay. I hope I am able to answer your question. Or, yeah. Ah. Okay, got it. So in a telco world, it is under control of the operator, right? So he will only decide it, he will deploy it. But I think, yeah, definitely this idea actually we think around it, how a user could play this important role, that what model he should be deployed for him. Actually, there should be some metadata. Yeah, definitely we'll try to think around it, yeah. Thank you. Could you repeat? Huh? Okay. So, okay, I'll go back to this architecture. Okay, I think this architecture will help you to understand them, most of the things. So here you can see the XApp and XApp is running at the near real time. Okay, so that is the closed loop here. Okay, near real time, and the use cases where the time sensitivity doesn't need, you will put it here as a RApp. Okay, and there are the interfaces. You can see this E2 interface. It is retrieving a real time data. There is a O1 interface. Where exactly it is? Yeah, so this is the O1 interface. So those are retrieving some less time critical data, okay? So the architecture is defined in such a way that the real-time data, you fetch it, and you use those real-time data to predict the value. And based on that, you will understand that what parameter you need to optimize. And around that, there's a service models defined in the specification, service model, E2 SMA specifically. So that using that service model, you can directly go and you can configure your DU, RU, and CUs. Okay, so that is the one concept. Okay, actually, I'll just expand it further. So once you collect the data over the O-RAN interface, right? So in O-RAN interface, there is a project called OAM. So they have defined the data models. Okay, so using that, they retrieve the data from those NFs, I would say, if you are familiar with the concept in the VNF. So from those NFs, actually, it extracts the data using those data models. Okay, and now the data is available here in the here available. Okay, now you'll take that data, you will train your model, and yeah. For me, now it's the data, right? Only I need to understand the data model. It's like everything is standard driven. So data model is available, I'll able to understand it, right? So I'll train the model. And here you try to understand what things we could generate. If you train the model, you can generate the policy. You can predict the value. You can generate the models. And that model also, there's some possibility that over the A1 interface, you pass it to near real-time rig. It will deploy as an XApp. Now the other XApp could use that model. They will predict the value. So there are a lot of possibilities are there. You can predict the policies, and you can pass the policy using the A1 interface to the near real-time rig. And based on that policy, again, he will able to configure the network. So they are this close up. They work together to optimize your network. Okay, thank you for the discussion. Yeah. So any other questions? Okay, sure. Okay, so thank you, everyone. Have a nice Cube day.